Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the screening effect or shielding effect. Let us understand what is screening or shielding effect. I have written some theory. Let us first read that. In a multi-electron atom, comma, the electron of the valence shell are attracted towards the nucleus, and also these electrons are repelled by the electrons present in the inner shells. On account of this, what will happen? The actual force of attraction between the nucleus and the valence electron is somewhat decreased by the repulsive forces acting in the opposite directions. So, this decrease in the force of attraction exerted by the nucleus on the valence electron due to the presence of electrons in the inner shells is called screening or a shielding effect. Let us understand this thing diagrammatically. Here you can see that we are having nucleus in the center. This is the valence electron, or you can say this is the outer electron. This is the, I'm writing valence electron. Now this electron, this is the inner electron. Here you can easily observe that the valence electron is having attractive forces with the nucleus, but at the same time the valence electron is also having repulsive forces by the inner electrons also. So due to which, what will happen? The valence or the outer electrons are not experiencing the nuclear pull which the nucleus is capable of. The outer electrons are getting attracted by the nucleus, but at the same time these electrons are getting repelled by the inner electrons, due to which these valence electrons are not experiencing the nuclear charge which the nucleus is capable of. That's called screening effect. So let's come back to the points. Now, the magnitude of screening effect depends on the number of inner electrons. That is, higher the number of inner electrons, comma, greater shall be the value of the screening effect. Now, the screening effect is calculated by the screening effect constant determined by the Slater rule. So let me write some rules for you to understand this concept in a better way. So first of all, I'm writing the screening effect constant. The screening effect constant is represented by a symbol sigma. Now I'm writing some rules of the Slater. That's, I'm writing Slater's rules. The very first rule: write the electronic configuration of the element in the following order and group them as. Write the electronic configuration of the element. Write the electronic configuration of the element in following order. And group them as first of all, I'm writing the first group, it's 1s, the second group 2s and the 2p, the third group 3s and the 3p, the fourth group only 3d, the fifth group 4s and the 4p, the sixth group 4d and the 5f, the sixth group 5s and the 5p, the sixth group 5d and the 5f, the sixth group 6s and the 6p, etc. and the etc. Now I'm coming to the second point. Suppose we have to find screening effect constant of screening effect constant of electron present in 4s 4p group. So I have just fixed a point that electron is present in the 4s and the 4p group. So what are the different sets of rules to find the screening effect constant? Now, the very first thing, I'm coming to the third point. Electrons to the right of 4s and the 4p, the electrons to the right of 4s and the 4p group will not be effective in screening, will not be effective in screening. Why so? Because first of all, let me mark the electrons which are present at the right side of the 4s and the 4p will not be effective in causing the screening, because these electrons are not the inner electrons as or with respect to 4s and the 4p. Sorry, the electrons which are present on the right side groups of the 4s and the 4p are not inner electrons with respect to the 4s and the 4p, so there will not be any screening effect by these electrons. So now let's come to the point number 4. All other electrons. Now all the other electrons of 4s and the 4p, because first of all we have to find a screening effect constant of a single electron present in 4s and the 4p. So there must be some another electrons also in the 4s and the 4p. So all the other electrons of 4s 4p group contribute to the extent of extent of 0.35 each to the screening constant. I'm going to solve some questions at the last of this topic. There you will get how to evaluate that. So first of all other electrons of 4s and the 4p group will contribute to the extent of 0.35 each to the screening constant. Now let's come to the fifth one. All the electrons in n minus 1 shells. N minus 1 stands for, here what is n? In 4s and the 4p, what is n? The n is the 4. So the electrons present in n minus 1, that is 4 minus 1, comes out to be 3. So all the electrons in the third shell with respect to the fourth shell, all the electrons in the third shell will contribute will contribute 0.85 each to the screening constant. Now Let's come to the sixth point. All the electrons which are present in lower shells than third shell. Now, what is left? If n is my 4, we are talking about the electron present in the fourth shell whose skinning effect constant we have to evaluate. If the electron is present in the fourth shell, we have talked about the third shell in the point number 5. Now we are left with the first shell and second shell. I'm talking about these two shells. I'm talking about the electrons present in these two shells, how much they will contribute in the screening effect constant. So all the electrons which are present in lower shells other than third, let me make this thing, other than third shell will contribute 1.0 each to the screening constant value, to the screening constant value. Now let's talk about this seventh point, and it's also very important one. The seventh point is different from the rest. Now I'm making some another condition. If we have to find the screening constant, I'm writing, if we have to find screening constant for the electron present in D or F subshells, then there is certain set of rules. I'm writing, then all the electrons in the group, I'm writing, then all the electrons present in the group lower than that of D subshell will contribute a value of 1.0, will contribute the value of 1.0 to the screening constant sigma, and other electrons of D subshell will make a contribution of 0.35, will make a contribution of 0.35 to screening constant. So these are the Slater's rule that I have written. You will understand this rule by doing some numerical portion. So let us start with a very simple one. Let's talk about the lithium first. Lithium. What's the atomic number of lithium? Is 3. The configuration will be 1s2 2s1. Here we have to find the screening constant for the electron present in the 2s. So that means we have to find a certain values for the 1s, because the electrons present in 1s are the inner electrons that will shield the 2s electron. So here what is n? Here n is 2, so here n is 1. That is, the rule is of n minus 1. You can see that here the rule is of n minus 1. So here we have to follow the fifth point. Here we have to follow the fifth point, the n minus 1. So it will make a contribution of 0.85. Here I am writing the fifth rule. How many electrons are there in 1s? 2. These two electrons will make a contribution of 0.85 to the screening effect constant, and this comes out to be 1.7. The value of sigma, the screening effect constant, comes out to be 1.7. So I hope you got this thing first. We have to find the screening effect constant for the electron present in the 2s. So the inner electrons are present in the first shell, so it's a rule of n minus 1, because the screening effect constant has to be calculated for the second shell. So we have to evaluate for the first shell now. It's 2 minus 1, that's why it's 1, so it's a rule of n minus 1. I'm following the fifth rule, and the fifth rule states that all the electrons in n minus 1 shell will contribute 0.85 each to the screening constant. So I have multiplied, the number of electrons are 2, I have multiplied this 2 by 0.85. I got the value of screening effect constant to be 1.7. Now let's calculate for the sodium now. I'm taking an example of sodium now. What's the atomic number of sodium? It's 11. The configuration will be 1s2, 2s2, 2p6, and a 3s1. So let's mark certain things. We have to firstly evaluate the screening effect constant for this electron, which is the outermost or the valence. So here n is 3. Here the n is, the rule is of n minus 1, so it is 3 minus 1 comes out to be 2. That means for these 8 electrons, the 2 and the 6, for these 8 electrons we have to follow the rule number 5th. Now let's come to the 1s. Now this is the innermost. Let's come to the sixth point. Here we are going to apply the sixth point. All the electrons which are present in lower shell other than the third shell, here because I have taken the example of fourth shell, so I'm talking about the third shell over here in the sixth example. But here in the sodium, my main n is 3, so the first innermost is the second shell, then all the lower shells, here the lower shell is only 1s. So this will, I'm writing first of all, here I'm applying the sixth rule. So these two electrons will make a contribution of 1.0. How many electrons are there? 2. So 2 into 1.0. Now let's talk about the 2s and 2p. We are having total of 8 electrons. How much contribution will be there? It will be 0.85. On adding these two, I got the value of 8.8, which is the screening effect constant for the electron present in the 3s subshell for the sodium. So here n was 3, so n minus 1 comes out to be 2. I have applied fifth rule for the 2s and the 2p. Now the innermost comes out to be the 1s, so we have to apply the rule number 6. So I have multiplied the number of electrons by 1.0. So now let's take some another example. I'm taking the example of potassium now. Let's take the example of potassium. Potassium atomic number is 19. The configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, and the 4s1. Now here let's talk about again the shell number. Here the shell number is 4, so this is the rule of n minus 1, so that's why it's a 3. That means I have to take these 8 electrons and have to multiply with 0.85. So I have applied fifth rule over here. I have applied fifth rule over here. Now all the left one, these all are most innermost electrons, and I'm applying sixth rule over here again, and sixth rule states that all the electrons which are present in the lower shells will have a contribution of 1.0 to the screening effect constant. So that means I'm applying first of all I'm adding up the total electrons is 6 7 8 9 10. I got the 10 electrons and I'm going to multiply it with 1.0. So 10 into 1.0 plus 8 into 0.85, it comes out to be 16.8. Hopefully you got this thing. We got the screening effect constant sigma for the potassium, for the valence electron of the potassium. Now let's take another example. Let's take the d electron now. So I'm taking an example of zinc. Its atomic number is 30. So configuration will be 1s2, 2s2, 2p6, 3s2, 3p6 and 3d10, then 4s2. Here I have to evaluate the screening effect constant for the 10th electron of the 3d. I have to evaluate screening effect constant for 10th electron of 3d. That means here 9 electrons are remaining. 9 electrons are remaining. So now let's come to the 7th point. It says that if we have to find a screening effect constant for the electron present in the d or f subshell, then first of all read out this line. Other electrons of d subshell will make a contribution of 0.35 to the screening effect constant. So here 9 electrons are remaining in 3d, so I have to multiply 9 into 0.35. Now let's come back to the 7th point. Here it all states that all the electrons present in the groups lower than that of the d subshell will make a contribution of 1.0 only. It's a special case when the electrons are in the d subshell. So here these all are the electrons that are in lower shell than 3d. So total electrons are 6 7 8 8 and 6 14 15 16 17 18. We got total of 18 electrons and its contribution is 1.0. So 18 into 1.0 plus 9 into 0.35, it comes out to be 21.15. The screening effect constant value comes out to be 21.15 for the 10th electron of 3d for the case of zinc. So these all were the cases. Let me make you understand screening effect again with the help of the diagram. Screening effect states that the valence electron, firstly let us understand about the valence electron. Here valence electron is this one. Here the valence electron is this one. This electron feels the force of attraction by the nucleus and feels the force of repulsions from the inner electrons. So what will happen due to which? What will happen? The valence electron will feel less nuclear attractive forces due to the repulsive forces by the inner electrons. That's called screening effect or the shielding effect, and we have calculated their values also. This effect is going to be very helpful in calculating the trends of atomic size, ionic radius, ionization enthalpies, electron gain enthalpies. So this effect is very important to understand that points. In the next lecture I'm going to make you understand the effective nuclear charge. So that will be also a very great topic and linked to this topic, the screening effect and the shielding effect. If you understand the screening effect and the effective nuclear charge in a very correct way, you will be able to calculate yourself the trends of the all other properties, that atomic radius, ionic radius, ionization enthalpy, electron gain enthalpy, electron affinity, electronegativity, etc, etc. So that's all for today. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then he/she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.